what's up everyone, and welcome to Motion Control with Unreal Engine. Today is a fundamentals day. We're gonna learn the protocols. Even if you don't really care about the protocols, it's going to help you when you start programming for Unreal Engine. So what today we're going to look at is, yes, we're going to talk about PWM and PPM, but we're going to focus on SBus and CAN bus. So just a short recap. What we did before, literally went through the whole protocol on MIDI. We did hands-on some MIDI with Unreal Engine. I fixed the serial.com plugin for Unreal Engine so we can communicate not only with MIDI, we're going to communicate with pretty much everything that we're going to see here. And this is going to be one of our tools that we're going to use to communicate from Unreal Engine to the outside world. That was the whole purpose of revamping the serial.com communication plugin. Okay, so what we're going to start doing on this tutorial is we're going to try to control pretty much everything from Unreal Engine. The basic idea is not to use any separate software or any separate solution. I want to be able to actually do everything from Unreal Engine because we can. And we're not pushing the limit. We have all the tools inside Unreal Engine to do this. You know, our dream is to manage one of these big systems, which, by the way, they have their own motion control system, of course. Each one has their own minutiae. They have their own protocol management, but guess what? Most of them actually use the same way of communication. That's what we're going to see right now. And I want to acknowledge one of the things that not really caught my attention. I heard about EDELKRONE doing exactly what we're doing right here, right now. Literally, they released the video, I think like 4 days before I released my first video on motion control. I can assure you, I can't do that video in 4 days. So it's not like I try to mimic EDELKRONE. Like, I've been working for at least 4 months on this. For me, this is validation of that I'm not crazy. Not only is needed in virtual production, but also is possible. I shoot an email to EDELKRONE. First off, I ask simple question if their system is open, if we can put more different devices on their system. I don't know. I'll let you know what they say. And then on this series of tutorial, this is pretty much what we're going to use. This is the range that we're targeting. Even the sliders are the cheapest part. And yes, Session was my first option. It was pretty much the first one that I hacked and tried to figure out the whole protocol. But I got into some issues, and the problem with Session is that there is not too much documentation. When I'm saying there is no too much, there's not documentation at all. But on the other side, DJI has a lot of documentation. Not everything. Like, I wish they have more, but at least they do have documentation. You know, one of the most difficult part, which is trying to figure out on the CAN bus communication, what is the data they're transmitting? Because CAN bus could be anything. Like, it's very device specific. You use the protocol for transmitting the information, but every manufacturer, everyone, it's different, right? But at least DJI, they have some white papers on how to use the CAN bus, and that helped a lot. So I got this DJI running. It's used. Let me tell you, this saved my life because everything is open. I was able to find pretty much everything. So the Session, I think they're copying DJI. I figured out later what was going on with Session. I'm going to keep going with DJI first. And once I strip out everything from DJI, I think it's easier to jump to other devices and other brands. Even EDELKRONE, in my imagination, I think it's just simple. It's just a PWM or PPM, and that's it. So, and you know, again, EDELKRONE developers, if you want me to send the information, it's going to be easier for me. Now, let me point out that even though I'm choosing DJI, it's not the cheapest alternative. Like, when you go pro, these are the prices. Yeah, of course, you have like a 3-axis and 2-axis master wheels, which is amazing and high quality, and everything is high quality, even this controller. Yeah, it's not like I'm choosing the cheapest option. The cheapest option should be still Session, but still I'm going to start with DJI because as a developer it's way easier, pretty much the reason. And this is the workflow that we're using right now. So we go from MIDI to Unreal Engine to microcontrollers to sliders and gimbals. That's what we're doing. That's what we're gonna do. Okay, let's do it. Okay, so in order to understand what we're doing, we need to understand what we actually control. So the end of the line always going to be the motors. It's going to be through PWM or PPM. This is pretty much the last thing that we are going to control. And that can be controlled by or an SBus controller. You can control via SBus directly to PWM or PPM, or go to a CAN bus, and the CAN bus is going to control everything. And here in the middle could be a microcontroller, but actually sometimes you don't even need that. You can go from S-bus to PWM and PPM. So we're going to see all those scenarios. But so these are the two controllers, either PPM or PWM. This is what pretty much everything on motion control is using, from CNC machines to 3D printers, drones, hovers, cameras, gimbals, and sliders, and focus control, and robots. Now this robot, we're not going to use hydraulics. Could be a really good idea to use Boston Dynamics with Unreal Engine, but we're not going to do that. We're going to go with the traditional motion control. Okay. So PWM PPM is a very simple way to communicate. There's a lot of error correction. There's some, coming from CNC machining, where you can count if your stepper motor did the step or not. There's a lot of things that are hidden, and if you want to replicate all the feature of PWM specifically, it takes some work. But we're going to use some libraries for this. Today we're not going to talk about this, just for the simple reason that we're going to make one tutorial and straightforward with PWM PPM, and we're going to control the slider. So there's not much that I'm going to talk about PWM and PPM on this episode, but just be aware we're going to jump straight to this on that tutorial. Okay, but yes, we're going to talk about S-bus and CAN bus. Now here's the thing with S-bus. S-bus comes from the radio control, remote control system for hobby. And one of the things that happens in the hobby industry is that it's pushed by companies that they're not necessarily on their best interest to release a lot of information. And the reason is, I have no idea what it's an old mentality. Let's put it like that, okay? And so there is not a lot of real information on the S-bus system. It's always one dude on the internet discussing with another dude on the internet, trying to reverse engineer what they're doing, and that causes a lot of confusion. If you try to get the real information on FUTABA on the S-bus, you're gonna try to find the source, and this is pretty much it. This is the only source that you're going to find. You're not going to find another article or explaining actually how it works, because it is more complicated than this I'm going to show you. And that's a big problem. That's a big problem when you're trying to do an open source project. What the FUTABA system is doing, in order to make it incompatible with pretty much everything, they invert the signal, okay? Which is the opposite of serial communication is doing. Inside the RC community, they call this the normal one, and the FSKY, which is the normal one, they call it invert. And the reason is that FUTABA was more common, and when FSKY came out with their system, so from the get-go, the inverter is called normal and the normal is called inverter, and that's where a lot of problems come. And especially when people start programming on the times where drones came out. Those drones were using these systems, but they're still using this system. They cause a lot of confusion. Not sure if they want to cause confusion, but they did, and it became a big problem for developers. Okay, and part of the information is how you have to invert the signal. These are three common ways to invert the signals. So what I'm going to use, I'm going to use the same one, and the reason why this is so popular is, one, because it's cheap, but the second one is it uses all the systems. So either you do a FUTABA or inverted, you're gonna have it here. So this is how I'm going to connect. So I gotta switch to S-bus. You can see it, put a picture there. Okay, so channel 1 is gonna be pan, and channel 1. Channel 2 gonna be tilt up, tilt down. Okay, in channel 4, because look at this is channel 4 is roll. Now, one of the things that a lot of people is trying to do, and they're not able and not gonna be able to do, is do the focus control with the S-bus. It's not gonna happen. It's not gonna happen because it's a CAN bus control. It's not gonna give you precision. You're sending information on how much you want to move, but there's no precision on this. CAN bus has precision. This one, nah, not that much, but it's very useful because yes, on the other side you can know exactly where the position is with CAN bus. So yeah, so this is one way of controlling. The only reason we're going to use this is to sniff the communication and know exactly what's going on, and look that information, this information, what's going on the oscilloscope. So that's our next step, is to connect all this stuff to the oscilloscope. So I'm going to use this to send the information to the receiver. It's going to go through all this mess, and then cable goes directly to, you just have to make sure this is on the S bus. And actually, this is the only way to communicate with the S bus and CAN bus. There are other connectors, but it's not going to work. Actually, this is the only way to do it. You have to get this wheel. And I'm using two digital analyzer because one is showing you things that the other one is not. Again, I just show you everything that I'm using. I'm using this Digiland. Now, if you are into electronics, don't always go for the big oscilloscope. It's not all the time necessary. Actually, when you have to analyze data, these are the best way to go. I have a Rigo here. It's not the greatest, it's not the worst, but it's very limited on the logic analyzer part. And things like this helps a lot. Even the logic, the red one, the CLI, I don't know how to pronounce it. You can write scripts and you can do your own logic analyzer script, which is really cool. Also happened with the Digiland. I'm going to go through the both so you see what I'm talking about. So we're going to sniff the communication. This is going to be the setup for the CLI. How you pronounce this shit? CLI. Key things that you need to set up is it's going to the bit rate is going to be 100,000, 8 bits, 2 stop bits, and even parity. The way that this is named is 8E2. When you say that 8 is for 8 bits, E is for even parity, and 2 is how many stop bits you have on the protocol. And this is important too. The most significant bit sent first. So the first bit that you see is going to be the highest bit. Okay, so we're going to start doing it. Before we start, let me clarify when I was talking about the confusion that there is on this protocol. You're going to find a lot of information. But one of the two biggest articles is this thread on the ARM forum. With the information by the get-go, it's wrong. So you're gonna start like me going back and forth. Oh, what's going on here? Like here, it's telling you is F0, the first byte, and here another information which is this is everywhere is telling you the 0F. Okay, it's not the same. Even though they say it's inverted, it's going to give you, the inversion is going to be 0F. It's not the same. When the setup is the setup, the result always has to be the same. You're going to find all these inconsistencies. This is going to drive you nuts. And I think the reason is because there is no chip company, nobody's actually publishing a documentation with 100% accurate information. Again, everything is one dude on the internet and versus another dude on the internet. And now you're going to have a third dude on the internet telling you two different things. But to be honest, this dude on the internet is right. Okay, so whatever he say on this video, he is right. And I triple check everything what he say. Even though I have some problem with that, I'm not even gonna mention because it's just pointless with that thing that I don't agree with. All this information, it's 100% correct. Just trust this dude on the internet. Don't trust the one. So yeah, but when it comes to documentation, there is no official documentation, and that drives me nuts. And everything is like this is one of the most relevant results, and when you look into the details, it's wrong, and that drives me nuts. Whatever. So I'm gonna go to a scope, and I'm gonna do the auto set because it's the best way to do it. So this is gonna be the only accurate information. There's only one channel what is we're gonna use on S-Bus, and this is the signal. Now I'm not gonna bore you to death. To analyze this, let's just go to what I already did before, which is took a lot of time. Let's analyze the protocol. So you have the information that this is an 8-bit even and 2 stops. Okay, this is the setup inverted, and the most significant bit, which is the highest bit, is going to be this one. Okay, so let me bring our old friend. This is a window calculator. If you don't know, there is an option here. You can go to programmer. You hit this is a hex values, or you can go to binary values. Click here. There you go. Really fast, we're gonna analyze the information. The most significant bit, in this case, those are 8 bits, right? So this is the most significant, which is the value. You can see 128. Okay, 128 is the maximum. This 4 is they're empty, and then we have 1 1 1 1, and the value is here 15. It's not gonna count the 0, but it's 0f, and that's what we have, 0f. If you have this result, your setup is correct. You have 1 start bit, so this is not gonna count. Then you have to the 8 bits. Then you have a parity, an even parity. Then you have two stop bits, it's this one and this one. And then you have a start, and then you have the next byte. So that's going to happen all along this stream of information. So again, if you have a 0f and a 15 value, this is correct. So this is your way to figure out if your logic analyzer was correct. The way that SBUS communication works, it's going to send 23 bytes, but if you try to read this, you're not going to be able to actually read the actual value because it's tricky. What the actually message is 23 bytes, but each part of the message is 11 bits long. It's taking 8 bits from the first byte and 3 bits from the next byte, and so on and so forth. It's going to start shifting all along. You see how it shifts. So you have to recalculate the information to know what the actually value is. The value stuff each byte is not going to make sense, even though sometimes it's the same value. You have to recalculate this. You can't read this on a serial bus and know exactly the final information. You have to recalculate the bytes. So you understand that you're going to be able to read with the Arduino serial communication what's really going on, but you're not going to get to the actual value that you actually need. So here's a good example. I'm sending all this information on maximum values, and even though it's a maximum value, it's not going to send me a back. So the maximum of each value is at 2047. The maximum value that this controller is sending is 2008. So you can see how I'm grabbing the first 8 bits, and then I grab the last 3 bits from the next byte, and this is the information that I have. Same for the second one, but if you pay attention to the numbers, this is H20, so a hex 20, and the next byte is hex 7. They're not matching, but they're not going to match because you have to do this shifting basically to figure out what the real information is. That's the complication on the SBUS communication. It's going to be a lot of programming basically to shift the bytes and get the information. Okay, so at the end of the message, you're going to have another byte that we're going to count it as a 1 byte. There's no shifting here. And then your end byte is going to be zeros. That's pretty much it. That's the SBUS communication. The rest is going to be actually hands-on the protocol and different tutorial. But let's jump now to CAN bus, which is a piece of mind because it is done by engineers. Actually, this was done by the Bosch company, which is a German company. Don't Google their history, or do, I don't know, you decide. But yeah, this was done a few years ago in the 90s. The beauty of this protocol is it's highly engineered. We are not going to have problem with inverted or not inverted, because guess what? We have both. You have both at the same time, so that's what it is. That's what CAN high and CAN low is. This is done on many others communication protocols. This is to cancel noise. There's a lot of electrical reasons why you're going to do that, but yeah, you have the high and the low at the same time. They're level on 2.5 volts, and they go from 2.5 to down to 0, and the other way around. Like I said, it was developed in 1986 on this window. I think I made it up, but this is a very well thought communication protocol, and basically it connects those two high and low. There's only 2 cables that goes to the protocol, and it sniffs basically like an oscilloscope all the information and communicates at the same time. There's a lot of communication between those lines. Now, so you have an idea, this is used on every modern car. It's used on the casino machines, it's used on trucks and heavy equipment, it's used on drones, building systems, for heater, for whatever you can think of. We have, of course, our little devices. It's used on industrial automation. It's used on medical devices. It's used on car manufacturing. It's even used on rocket science. You get the idea. It's very trust communication protocol. Now, the reason why it's so very trust is because it has all these features, which is bit monitoring, bit stuffing, frame check, acknowledgement check, and CRC, which is a cyclic redundancy check, which is error correction. All these things work together to make sure that the information that you send is the information that you get. And the good thing for us is that DJI has documented this very well. So they have that information on white papers. Not every DJI product has this information, and I already figured out that it's not the same information, but at least you have an idea of how they use the CAN bus protocol, because CAN bus is very device exclusive. Every manufacturer is going to put the information that they want. I think every model, because in this case, this is not matching what I have, the DJI R. It's not matching what I have on the Ronin S, but it's matching some of the information and what kind of information it's sending. So at least I have an idea what's going on, and that's good. It's pretty much what I'm using DJI. I would love to have the session information, but for now we're going to start with DJI. So again, DJI is at least good communicating what they're using. So a lot of the guess is easier. It's not that we're not guessing actually. And this is what it looks like. It's very clean signal. You have the high and the low signals. This is how we're going to connect. Remember to move to CAN. And before I start breaking down CAN bus, I need to explain you this. This is very, very important, which is bit stuffing. If you go to an oscilloscope and you don't have a CAN bus protocol analyzer, you're going to see the information, but you're not going to find out what really is going on. Okay, so bit stuffing is going to happen every time you have more than 4 zeros. If you have 5 zeros, it's going to send another bit reverse of what you already have. Okay, so if you have a 5 0, it's going to send a 1 on the next bit. If you have 5 1s, it's going to send 0. And the reason is because this protocol doesn't have a clock. The clock is kept with the information that we're sending actually. So if it has more than 4 bits without a reference or a change, it's going to push to do it no matter what. So this is a typical example with zeros. So you have 1, 2, 3, 4, 5, and the next bit is going to be high. This particular protocol analyzer is telling you that this is bit stuffing. And the funny part, the most expensive is not telling you that. So it's not showing you that information. That's why I wanted to show you the other one. That's why sometimes you need more than one to actually have the whole picture, at least to explain it. If you know, you know. But this bit, when you're going to see it on the rest of the information, so you know it's not going to confuse you, ignore it, like the protocol does. And the other thing is, if you write a protocol, you also have to do the same thing. So you're responsible for doing the bit stuffing too. Yeah, that's something you have to think of if you want to actually make a CAN bus protocol library on Unreal Engine. You have to go through all this. And those are one of the issues. There's more that we're going to see later. Okay, so let's go for the first byte. The first byte is going to be the arbitration field. This is going to tell you what is the ID that you have. So from this point, you know if this is a focus encoder or if it's a movement or what. We have a start bit, and then you have 11 bits identifier that we're going to count it like this. So as you can see, it's not fixed. It's not 8 bits all the time. So this is going to change all the time. So in this case, this is 11 bits. There's also 29 bits, but we're going to use the 11 bits. And on this information, the control frame, that's how many bytes the protocol is going to send. So this is very important to know how much information is coming after. Each CAN bus message is specific to the device that you're sending from. And then you have, in this case, it's going to be 8 bytes. Boom, straightforward. 8 bytes. You see some bit stuff in here. So, and this is how it looks like on the protocol analyzer. And there you go. You got the high and the low. Let me put it on the same level so you get a better idea. It's a beautiful protocol and everything works. And we can go to our protocol. Let me stop this one. Okay, so this is the code information. This is very difficult to see it on a bench oscilloscope. Logic's analyzers are beautiful for this. As you can see, each one of the ID represents each one of the stream of information. And what I want to show you is actually the wheel. Technically, one is for zoom and the other one is for focus. We're going to use 531 filter by ID. Let me clear it up and show you all the information. If I move this, you can see right here, look, I start moving, you see, 6, down, up, down, up, down. And this also changed. This is a very fine amount of information. But yeah, that's how you figure out what each thing is, right? And I'm gonna move forward and I'm going to decode the rest, but at least you know how to decode things on the Canvas protocol. In this case, I'm filtering everything on the wheel. These are the 3 streams of information. This is the ID pretty much, because there is no movement here at all. When the CRC doesn't change, it means that it's the same information all the time. And that's how you decode basically each one of the package on Canvas. And the CRC information is going to do the sum check. If you want to do it by yourself, that's the information. It's too much for my brain to calculate the CRC, but there is a lot of documentation. Bosch has, and I'm going to put it here on the description too. And also there is some C code, where C++ code. So you can run CRC, and this is an online check. The beauty of this protocol is that you always can have accurate information, and there's many ways to check all the error that doesn't happen on FSKY. On FSKY, you lose a frame, something happened, boom, you're done. Canvas, it's very precise. There also, at the end of the package, is going to be an acknowledgement, which lets you know that you receive it or not. So if it's not checked, your device is going to keep sending it. And at the end, it's going to be a series of 1. It's going to be flat line. This line never going to go down until the next message. And some of the Canvas extra considerations, MCP 2515 is one of the most popular Canvas chip that is used for decode the Canvas protocol. Yes, you can do it on the microcontroller. You could do it like directly without using any of those chips, but you have the advantage of quality control. Basically, the code could be tricky sometimes. This chip is taking in consideration a lot of things that you're not, if you want to do your own protocol decoder. And the funny thing about this chip, I talk a lot with Microchip on conventions and all the stuff, whatnot. As a matter of fact, it's one of my favorite chip companies. I don't work in Microchip just because I don't want to go to Phoenix. That's the only reason. But yeah, it's a great company. Engineers are very open. They're very accessible. You can actually call them if you have any question. They're going to answer. Oh, someone's going to get you back. I love Microchip. This is a weird thing. Piece of data that I'm getting for you is the reason why this chip is so popular is because it was part of Arduino Shield. So think about this, how simple things like Arduino, which by the way they acquire Atmel, how an Arduino Shield boosts your cells. It's amazing. Someone decided to make an Arduino Shield with this chip. It's not because it's the best, there's a lot of flavors in these chips, but the truth is because it was part of an Arduino Shield that it became popular. So if you think about it, for all these manufacturers who, we want to decode their protocols, it's not a bad idea to be open. I mean, it's just food for thought. Anyway, some of the consideration is, so here's an example, sending a lot of bytes, a lot of information. This happens once in every 60 milliseconds, and all this information is sent at once. You see all this, how the levels goes up. And this is kind of dangerous because if you keep doing this, your zeros is going to become ones. You gotta be careful how much information you send, and you gotta do a stop. So this is an example over time, and this is that stream of data. Look how long it takes to go down. So that's dangerous. If you keep doing this, your zeros are going to become 1, and then you're going to lose all the data. Something you have to think about if you're doing your own Canvas transmission. You gotta think about it's basically impedance. You can change it with a lot of capacitors, but it's something you have to think of. So this is 64 milliseconds from the time that you finish sending all this stream of information. And they know that. That's why they're sending not so much information here in the middle. So something you have to think about. Okay, wrapping up. The idea is to decode everything we can have on hand. DCI and Cision, those are the two main, and then there are going to be a lot of off-brand things that we're going to use, like sliders and whatnot, whatever. And we're going to start mixing and matching everything. Like, doesn't matter what brand it's going to be, The idea is to be brand agnostic and be able to decode each one of those. So I'm gonna need a lot of help, and that's why I'm showing you how to decode that information, because most of the information that I can give you is, how much I can spend on equipment and how much I can, people help me too. That's why this is open source. Whatever you want to contribute, if you have the tools to analyze your canvas on your equipment, it's going to help a lot. And manufacturers too. I would love to have manufacturers give me, like DJI already sent an email. They answer in a week or so, but they answer. If Cision, help us, it's going to be faster for us and it's going to be really good for them. And actually, this could be like a good trend for manufacturers to actually make something compatible with, so we can start adding their equipment to our open source system. There's a lot of brands, and like I say, they're going to have their own protocol and their own way to send the information. But slowly, we're going to go through them, and the idea is to make an open source system where you can mix and match all these brands, adding stuff that at the end of the day is going to be for everyone. Okay, so first I want to thank to Kaiser Hadi. He got the reward for the NFTs. He totally helped me. It wasn't easy at all. Like my question on the current aperture, all those values for controlling the camera, it wasn't easy. Even looking at the blueprints, it's not intuitive at all. Like you really have to dig in that. So I think I'm gonna make a short tutorial on how to get those, because I couldn't find any tutorial, and to be honest, I might be missing some of the famous tutorials, but I couldn't find it. So thank you guys here. And now we're talking about the NFT. There were a lot of comments about the NFTs. Look, this is not, we're not going into the NFT fever. This is an NFT project dedicated to utility part of NFTs, okay? This project is a twofold, basically. It's educational and at the same time could help as a collectible. I'm not pushing anyone to buy these NFTs. If you are a subscriber to the channel, you are entitled to at least one NFT for free. The other NFTs that I'm selling for literally $5 is like, I'm just selling it for $5 because I also want to learn how to work with the NFTs, which is not easy. I'm literally programming this NFT from zero. But the idea in reality is to test how NFT works as a key, as a digital key. If you don't like the NFT, don't get them even for free. I don't care. But I heard some comments where just stop. This is a project and they're collectible at the same time. They're NFTs, so it's what it is. And on that note, thank you to Chef Fush, who actually helped me to debug this. First off, thank you for buying NFTs. That's the first one. Like I really appreciate what you did, and thank you for debugging with me, because look, we're going somewhere with this. I think it's very important for everyone who's in this industry to learn how NFT works. Call me crazy, but I think in 5 years the NFTs, they're going to be part of our business. So I don't know. Thank you everyone who actually supported me with this, and thank you everyone who's helping me with NFTs. Okay. There's a Discord server with a lot of people working on Unreal Engine and virtual production. That's that. And thank you, and see you next time.